Hello and welcome to the University of Saskatchewan Space Design Team's Critical Design Review for the 2016 University Rover Challenge. The purpose of this video is to show how much progress we've made so far and to explain some of the design choices we've made for the upcoming competition.
This is our third year designing for the competition, and we have certainly learned a lot in the past few years about what it takes to design a successful robot. We were able to travel to Poland last fall to compete in the European Rover Challenge and are very grateful to have received first place for our performance.
And with our success, we've decided to take a little bit more risks. The great part about taking more risks with our designs is it's given us the opportunity to be more innovative, but we still will have great designs to fall back on if something doesn't work out.
During the last summer, we did extensive research on skid steering and rocker bogie suspension and determined that rocker bogie is still the best design for our needs, and that skid steering has the advantages of saving weight and being simpler to implement. The suspension design this year will focus on a foam core. The carbon layup is a mixture of unidirectionals going down the length of the suspension, as well as plus-minus 45-degree laminates to handle torsional loads. The suspension arms will be fastened to the carbon motor housings that we have constructed. These are also made from varying directions of laminates and have been successfully tested on our dyno for our motor operation.
We have finally switched over to brushless motors, which give us a lot more control and flexibility. This is a really significant change in the design and is going to have a huge impact in the performance of our rover. Some of our initial tests have been extremely promising and are really confident in the results this can provide us.
Alright, so when we decided to design the wheel, we focused on really three things: increasing traction, reducing weight, and simplifying the design. So kind of the evolution of designing a wheel came down from looking at previous examples on other rovers, like actual rovers. We created a set of pneumatic tubing and an aluminum rim for it to sit along with a customizable tread that would give them the best traction for the options that they'd need.
Yeah, in this new wheel, we added about 1 inch of diameter and about 1.5 inches of width. So there's a lot more traction on the ground and a lot more in contact with the wheel.
This year, we're using a new shell design that will optimize airflow. We changed the color this year because it absorbs less heat compared to if we use black. We're using new filters and have more space for various components of the rover.
One of the most important parts of the rover is the battery. And although we've never had any problems with the robot's battery in the past, we have realized that the battery is much too large and much too heavy for some of the advancements that we've made. In order to get the most we can out of the rover, we've built a custom battery system from the ground up. This system is still using lithium iron phosphate cells, which we have selected because of their safety when damaged due to a puncture or to a short. We've also integrated an open source battery management system. This balances the cells to get the most performance we can, while also monitoring their health to make sure that we don't do anything that will damage the battery or cause danger to anybody. Over the summer for ERC, we completely redesigned the rover software in order to take advantage of multi-threading and become a true real-time system. Not only does this make it easy to manage the performance of the rover, it also makes it easy for more people to work on modules at once and to add and remove functionality on the fly. It also should be noted that we switched from using a Raspberry Pi to using a Raspberry Pi compute module-based computer. This has given us an immense amount of flexibility in our electrical design, as we have complete control over all aspects of the computer system.
This year, one of the big projects that we've been working on is designing a new robotic arm controller. The purpose of the arm controller is to move a lot of the positional feedback to a more hardware-based approach. This gives us a lot more flexibility with the software, which allows us to hopefully do more complex movement with inverse kinematics.
To meet the new challenge of the equipment servicing task, we've made several improvements to our wrist and gripper design. The wrist design will be able to articulate so that we can facilitate unscrewing the oxygen regulator, as well as we have 2 gripper designs that are optimized for picking up and unscrewing lids.
The camera and communication system this year is seeing a ton of changes compared to URC in 2015. We are expanding our Oculus Rift 3D video with a auto-stabilizing brushless gimbal. At the same time, we're also exploring the idea of a 360-degree video sphere. We have a dedicated hardware video encoder module to give us low latencies and reduce the number of radios we must carry on the rover, and at the same time are upgrading our radio system. We were able to test this radio at the European Rover Challenge, which was an unbelievably noisy environment, and we're really looking forward to some of the testing we can do, as the radio system has some very promising characteristics for long-distance communication as well as multipath communication when out of line of sight. The science task itself offers a lot of opportunities for really innovative approaches. Last year we worked on developing a really simplistic laser spectroscopy system and paired that with a wet chemistry experiment on the base station. We uncovered some of the reasons for our failure and are going to redeploy that system with upgrades. Additionally, we'll be updating our probes for pH, moisture, and temperature. The soil auger also deserves mention. Using a soil auger with a better core catcher, this year we're progressing the design of the auger even further to use 3D printed plastic. Not only does this give us the flexibility we need to develop the proper auger geometry for the soil, it also allows us to replicate the auger as many times as we need and sterilize each auger before taking a sample. Finally, this auger will have a removable sleeve inside and has been designed to disrupt the dirt around it as little as possible. One big thing that we've come to appreciate is the importance of modularity in our design. Last year, we had some really good system architecture, and although we ran into some problems with a lot of our modules at some point, they had a really strong foundation to stand on. This year, we've made sure that all of the new parts are still backwards compatible with the old system. Unfortunately, at this moment, our rover is not driving, as we are still solving some of the problems with our carbon fiber suspension and waiting on the wheels, which do take extra time to manufacture this year. We are really looking forward to showing the progress of the project once everything starts coming together.
Thank you for watching the USST's Critical Design Review for the upcoming University Rover Challenge. My name is Jack Fotheringham, and I'm the team's president.
I'm Austin Shirley, VP Engineering of the team.
Hello, my name is Daniel Ness. I'm the Vice President of Operations.
My name is Nicole Parker, and I'm the treasurer of the space design team.
My name is Seamus Woodward-George. I'm the mechanical lead.
Liam Bindle. I'm the electrical team lead for the USST.
I'm Michael Kowalowicz,
I'm Blake Hopkins.
and we're part of the capstone team that's putting together the Mars rover wheel.
We hope the video gave you a clear idea of what we are working on this year, and we look forward to sharing our progress with you in the upcoming weeks.